Swayam Prabha, Digital India, Educated India.
Today's topic is PN junction, right? So before we actually go into the PN junction, what we can discuss, let us briefly discuss, right, how these PN junctions are fabricated. So if you see this picture, it is a typical flow of fabricating a PN junction. Now PN junction are part of means they are basically there. If you consider any semiconductor device, at least one PN junction will be there, right? So it is basically integral part. So we should know about the PN junction. Now, if you see the fabrication step, there are actually, in typical IC fabrication, there may be 50, 60, hundreds of steps, right? But they are basically few fundamental processes are there, which are combined in different permutation and combination, right? For example, let's say we begin with a piece of silicon wafer, right? The one we obtained from Jones-Ralski method that we discussed in in the beginning when we discussed crystal. So with that sample, now a beginning sample can be N-type or P-type. So at least in this example, it is N-type. So let's N-type, right? Now, if you want to form a diode, what we have to do? We have to basically make a P-type silicon here, right? Now, one way, of course, we take this piece of semiconductor and somehow inject holes from the top, then whole upper layer will become P-type, right? But that will not be useful because whole wafer working as one PN junction, not very useful, right? We want to make devices, right? So we have to choose some places where we want to make a PN junction, right? And we have to make the circuit also, right? So what we will do in this example, what we are doing basically on this, let's say this is the top view of the silicon. We want to make a few pockets, right? Let's say we want to make some n number of diodes. In this example, there are 4 of them. So we will make 4 pockets here. Let's do it. Let's say so 4 pockets here where we will make a p-type doping, right? So this substrate is n-type, and we choose 4 pockets where we will dope it n-type, right? So these 4 points will be basically 4 PN junction, right? Now, how do we do that? Since we cannot directly, inject the dopants, right, at particular location, we have to cover it, right? For example, if you recall that, during Diwali we have paint our house, right? So if some portion of the house we don't want to paint, right, we cover it with certain plastic or something, right? So similar thing is done here. What we do here, first of all, we oxidize the top surface, right? So this oxide basically acts as a barrier. Then we want to open some window through this oxide, right? So we want to selectively etch away the oxide. So how do we do that? We apply a chemical, right, called photoresist. The photoresist is basically a material which respond to the light, usually UV light. So UV light can make the bonds weak or it can make the bonds strong. So depending on that, these photoresist have a name, positive photoresist or negative photoresist. So for example, we apply a positive photoresist, right? Then once we apply the positive photoresist, then what we do, we make a mask, right? You see here, this is the mask. So in this mask, this black region is opaque and the white region is transparent. So UV light will pass through this transparent region and make this photoresist weak in these regions, right? So then of course we wash away the photoresist, and then we have the opening here. Now what we want to do, we want to remove this silicon dioxide also from here, right? So for that we use a process called etching. So this is called reactive ion etching. So this of course etching has to be selective so that it only removes silicon dioxide. It does not remove the photoresist or silicon, right? So these are the some characteristics that are required. Then once we remove the silicon, now we have the window here, right? So in this window we can dope this region with the material we want. So in this case with the p-type dopants, and once we dope it, then of course we have to remove the photoresist. And once we remove the photoresist, now we want to make a contact, right? Now we have made a PN junction and we want to make a contact. So what we do for that, we deposit metal here, right? Here it is on aluminum, but there are other metals also, and each metal has their region to choose or not to choose. But this metallization will basically happen as a blanket, right? So whole surface will be covered with metal. Now what we want to do, we want to connect it as per our convenience. So what we will do, we will remove metal except in these regions, right? So except at the opening of these four doped region, we will remove the metal, right? So for that, this we will use another mask. This is called metallization mask. So this is opaque at these four places and transparent everywhere, right? So again, same process using photoresist and mask, we can etch away the metal. So here we etched away the silicon dioxide. Here we etched away the metal, right? Now we have the contact at these points of PN junction. So this is basically the process. This is basically called the front end process, and the metallization and the interconnect, they are called basically back end process. So these are just names, so just to be aware of. So you see here, this is a simplified description of steps in fabrication of PN junction. So there are 4 diodes per wafer, and of course these diamonds are not to the scale, they are little exaggerated. Now if you notice here, there are actually few processes only, right? So you can write one process will be oxidation, another process will be etching, another process you can say is photolithography, another process called doping, right? Here is ion implantation. Then another process called metallization, right? So these are few processes that which are repeated. Now let's say you want to make it more complicated. Let's say in this N-type substrate, we have this P-type. Let's say this is your N-type substrate, right? Then we make P-type well here, right? You can make another N-type here, right? So this will become like PNP transistor, right? So again, you have to repeat the same thing again, right? To make the structure more complicated, right? So we can basically get whatever device we want by following the same processes in certain permutation and combination. And of course, these complex processes, they are basically automated, right? Because especially for the mask, we need the alignment, because if you miss the mask, let's say you use the first mask and second mask, they are not aligned, right? So then there will be an issue, right? So this alignment has to be very precise. So let us discuss these steps one by one. So any question? No? Okay. One process is basically thermal oxidation, right? So if you look at this chamber, this is basically the holder which is holding the wafers, right? Then this is the furnace, right? And this is basically heating coil surrounding it. Now what is done? This thermal oxidation is of basically 2 types. You can use dry oxidation or wet oxidation. The wet oxidation is usually much faster. The wet oxidation is much faster. So if you want to grow a thick oxide, we use wet oxidation. But if you want to precisely control, let's say you want to grow the gate oxide, then we will use dry oxidation. The quality of oxide is also much better in case of dry oxidation. So both can be done using this furnace. So in this furnace, the gases are basically injected from the gas inlet. It can be dry oxygen or with some water content, right? And they basically flow from top to bottom, right? Now here the wafer is basically placed here, and they are usually facing down, right? So that let's say if they are facing up, then particle contamination can deposit on them, right? So usually they are placed facing down, and this is high temperature process. So usually they can be heated in the range of 800 to 1000 degrees Celsius, right? And then of course they flow down and they exit through this chamber. And you can also see some vacuum pump is there to keep it at low pressure, so that impurities are not inside. And then if you understand this thermal oxidation, what is happening, let's say this is your piece of silicon. Oxide is growing, right? So when oxide is growing, it is taking silicon from the wafer itself, right? So some part of silicon will convert it into silicon dioxide. Now when silicon convert to silicon dioxide, the volume will expand, right? And there is 2.2 times volume expansion. So that means 0.44 micron silicon will give a 1 micron silicon dioxide. So a thickness of 0.44 micron silicon, when it is consumed, it will give 1 micrometer thick silicon dioxide. So overall volume of the wafer would have increased, right? Now this ability of forming silicon dioxide is the main reason why silicon electronics is so popular. This native oxide of silicon has very interesting properties. It's very stable, thermally stable, and it has minimum number of interface traps, so that the traps are very less. So it gives very stable and with good electrical properties. So that's why silicon is so popular. Other materials lack this kind of oxide. Now similar furnace can also be used for depositing oxide instead of growing oxide. Here we are growing, right? So in growing, it is taking the silicon from the substrate itself, the wafer itself. So instead of that, we can also deposit the oxide, right? And that is done in a process called CVD. Now CVD is chemical vapor deposition. There are two types typically. One is low pressure CVD, other is plasma NN CVD. So of course, unlike oxidation, they do not consume silicon, and they can be done at lower temperature. So and another characteristic is that since they are done at lower temperature, they have good control. So you can use them to grow thin films. In oxidation, it is little difficult, to precisely control the thickness. Of course, dry oxidation you can do, but it's very slow. So CVD is one technique, and sometimes the material may not be available. So for example, once you have made certain structure, right? So silicon may not be there, right? So in that case, you have only option to deposit the silicon dioxide. And also, let's say once you make the device, right, you want to cover it, right, with some other dielectric, usually silicon nitride. So that layer can also be deposited using CVD process. So for example, silicon nitride, polycrystalline, or amorphous silicon, so they can be deposited using CVD process. Now we have also discussed briefly about MB, MOCVD, right? So they are also kind of CVD, but they are very specialized and they are used for a single crystal growth. Now here these dielectric layers, they need not be single crystal, you know, but MOCVD or MB, they are very specialized process to grow a single crystal layer. So basically a defect free layer that are to be grown. So it is also done, you know, within the, you know, some furnaces there where heating electrode is there and gas flow there. You know, the gas that will flow here will contain silicon because now it is not taking silicon from the wafer, right? So the silicon is contained in compound form called silane, SiH4. It reacts with oxygen and deposit the silicon dioxide there. So this is CVD process. This is also used in fabrication. Now, once we know this, these two processes, the oxidation and CVD, we will understand how the carriers are injected, right? So one process is called diffusion. So you know, either you can diffuse the carriers or you can use ion implantation, right? Now this diffusion is basically an older process, right? In older devices it was used. So basically what was done, again a window is opened. This is your silicon wafer, and then some window is opened, and from that window these carriers are, these ions are diffused, or these impurities are diffused. Now of course, because it's a chemical process, there is a limit how many impurities you can diffuse through it, and that limit is called solid solubility limit, right? We will not have such kind of limitation in ion implantation, right? So there's a maximum impurity that can be dissolved. Of course, if you do it at high temperature, you will be close to the solid solubility limit. That's why process is done at high temperature, typically, you know, 800 to 1100 Celsius. Now another characteristic here is, because the doping concentration, if you see, it's ranging from 10 raised to power 14, 15 to 10 raised to power 17, 18, right? So this is basically, you know, now you compare this thing with the total number of atoms, right? 10 is to 22, right? So it's order of ppm, right? Part per million. So for 1 million silicon atoms, we are injecting one impurity. So that means purity is very important, right? Cleanliness and purity is very important. So the wafer and the source, they have to be very pure. Now source it may not be in atomic form. It may be some compound, right? Boron oxide, BBr3, or boron chloride, right? Similarly for phosphorus, PS3, phosphorus pentoxide, or POCl3. So these compounds are used for diffusing, diffusion purpose, right? Now of course these dopant, they will diffuse from high concentration at the surface to inside. So a high concentration has to be maintained. Now either you can deposit a layer and inject these carriers here, you know, grow a layer with some carrier, apply heat treatment, and they will diffuse. Or you can maintain a constant gaseous concentration of these dopant, and they will diffuse through the surface. And this dopant diffusivity is expressed as Arrhenius equation, where EA is the activation energy and D naught is the coefficient of the diffusivity. And if you apply this for certain time t, so the average distance these dopant will diffuse is root dt, right? It's very similar to the carrier diffusion, right? Diffusion length is root dt. And just dt is also called thermal budget, right? So D is basically controlled by the temperature. At higher temperature, diffusivity will be more. So, you know, either you can have a process at high temperature and for a small amount of time, or you can have a process at low temperature for longer time, right? So these are different variations, right? Then of course you can use those diffusion equation to solve and obtain the concentration profile. So here I give two examples. We are not going to going into solving the diffusion equation, but it's fairly straightforward. So either you can get a Gaussian distribution or you can get a complementary error function distribution. So Gaussian distribution is obtained when the amount of impurity is fixed, right? That means you have only n number of atoms, they are to be diffused. So that is called limited source. And if you have continuous supply, then you get this complementary error function distribution. And of course, the problem with this diffusion is basically because it's a high temperature process, it's difficult to control the profile, right? And being this process high temperature process, it will have limitation. Let's say you already have some doping, right? And if you do the diffusion, right, so existing doping will diffuse, right? So existing doping would have altered, right? So there's some limitation, and especially if you go for modern devices where these wells are of order of few hundred nanometer only, right? Diffusion will not be practical. So there is another method which is more precise called ion implantation. So in case of ion implantation, these dopant species are ionized here, and they are selected, right, using mass separator magnet, because the magnetic field, if they then according to the ratio of Q by M, these species will respond. So you can select them, right? And then once you selected the species, it is accelerated, right, with certain energy. Now this accelerated energy will define how much deep, let's say this is your wafer, right? How much deep these ions will go, right? And the depth of these ion is called projected range, RP, right? And once they go at the projected range, now since all of them will not reach here, some of them will go ahead, some of them will go stop before. So this half width is basically called straggle. So you will get some kind of this kind of profile basically, right? So now the energy of these ions is varying from few kilo electron volt to mega electron volt. Okay, and these terms you should be clear. RP is the projected range where the peak occurs, and delta RP is the straggle, right? So where 1 by E of the peak, right? So this distance is basically straggle. And phi is the dose of ions per square centimeter, because we are supplying the ions on the surface, right? So this dose is actually expressed as per square centimeter. And when it goes inside, when we talk of the doping is per cubic centimeter, right? So if you see here, the doping inside is basically given by this exponential or Gaussian type of function, right? It's a Gaussian function with average at RP and with delta RP as some kind of standard deviation, right? And the peak carrier concentration, peak doping concentration is basically dose divided by root 2 pi delta RP, right? So now it has the unit of per cubic centimeter. So that is the doping profile. Now, but there is a problem with this one, because when these ions are bombarding the surface, they will disturb the silicon atoms, right? And when these silicon atoms are disturbed, there will be some defects will be created, right? So to overcome this lattice damage, we have to do annealing, right? And this annealing, of course, will lead to some kind of diffusion. So it has some positive and negative points. Positive points we have already discussed. It's a low temperature process, and then you can precisely control the doping concentration, and you can precisely control the geometry. You can do the shallow doping also, order of now when do you do the annealing, then what will happen? This peak position will not change, but this will basically diffuse from the peak, right? So it will become something like this, right? So the delta RP will change, right? Now new delta Rp is given by delta Rp square plus 2 dt, right? So delta Rp square is given by original delta Rp square plus 2 dt. So this dt is the thermal budget, or root dt is diffusion length, right? So you get a by the combination of ion implantation and annealing, which lead to unintended diffusion, you get overall profile something like this, which is better than the diffusion itself. So how this this annealing is done? Annealing is done through rapid thermal processing. Now here if you see, this is the wafer. It is placed on these quartz pins, right? So the care is taken care that this region at low thermal mass, right? So that all the heat that is applied goes to the wafer only. Now what is done here? These are the tungsten halogen lamps which are used to heat the wafer. So they can basically produce the heat very quickly. So the temperature can rise very quickly with the rate of 50 to 100 Celsius per second. And then you apply for it few seconds, high temperature for few seconds. So either you apply high temperature for few seconds, which is done in rapid thermal processing or RTP, or you apply little lower temperature for longer time, right? Usually done in furnace, because furnace you cannot quickly raise up and down the temperature, which you can do in RTP. So with that you can have a better control of temperature uniformity and accuracy in the thermal budget, right? So if you see here the picture below, this is basically how the temperature changes, right? So during this region, for few seconds, high temperature, the diffusion takes place. So it basically corrects the sample if for any damage due to ion implantation, and settles down the dopant species to the lattice site, because it is possible that these dopant species may be occupying some non-lattice site, right? So they basically dopant species move to the lattice site. Okay. Now once we know these processes, there's another process called photolithography. Now photolithography, what it does, we use a resist, right? So resist is basically a polymer, basically organic compound polymer. So when it is exposed to UV light or high energy electrons, based on that it has a name, right? UV lithography or electron beam lithography, right? And there was one question also, right? If you use electron beam lithography, the wavelength will be very small, right? So you can do more fine operations. And then based on that we already discussed, the two types of photoresist, positive and negative photoresist, right? So in positive, whichever part of the photoresist that is exposed to the light or electron beam becomes weak and is washed away. In negative, it is the unexposed one. So exposed one becomes hardened. So, and the opaque region, they are made up of UV absorbing layer, usually iron oxide. And then mask is basically made up of quartz, where different regions are pasted with they're covered with different materials. It could be iron oxide for the absorbing layer, and other region can be transparent. So we will basically select, expose the resist, right? Now this exposition of resist is done through a system, right? So if you see here, this is optical stepper, where there is a light source here, right? And that light source is basically through these lenses, right? And these reticles are basically used for alignment, right? So properly alignment, and then they are basically focusing at certain point. But when this light or electron beam focus at certain place on wafer, um, there are two considerations here, right? One is because this is very narrow, right? So there will be limit of diffraction, right? So diffraction limited minimum geometry is given by 0.8 lambda by numerical aperture. Now numerical aperture is basically is a number, right? Which tells us the ability of a lens to resolve, right? Or basically it's basically n sine theta, right? The angular aperture of the lens. So it is related to the index of refraction of the medium between the lens and the wafer. So that of course is determined by the system, but the wavelength is related to the source. So of course, if you have a smaller wavelength, you can have a finer feature size, right? So that leads to EBM lithography application in in fabricating the devices where you need uh, a resolution of the order of few nanometer, right? So this is the resolution which is controlled by the diffraction limit, and another is a depth of focus, right? So how deep it is focusing, right? So that is related to again wavelength by 2 Na square. Na is the numerical aperture. So but when you go through the different processes, the surface may not be planar, right? It may have some kind of this. So what is done basically, the surface is planarized, and there are two processes, a chemical and mechanical. So mechanical is basically the polish, so you polish it, right? And then chemical is basically through applying chemical, it will react and it is passed through the surface. So surface is made planar, so that depth of focus address the intended result. So up to that particular depth, your resist will be weakened or hardened, right? Then another process is etching. Once you have a photolithography, we have to etch out, right? So in this the etching chamber, you can have single wafer or multiple wafer, and it is done through especially we are describing here um, the reactive ion etching, right? But reactive ion etching basically consists of two type of etchant, and traditionally this wet etching was used. It's also called chemical etching. So in wet etching, this hydrofluoric acid, it selectively etches the silicon dioxide. Now selectivity is very important, right? It should not affect the photoresist or silicon, but it has drawback that it is isotropic. So that means if you have a silicon dioxide layer here, right, what will happen, it will not only as the silicon dioxide down, it will also as the, so this is basically covered by photoresist, right? And this is silicon dioxide, so it will etch blue also, and it will etch in below the photoresist also, right? So this is called undercut. So this is called isotropic. Anisotropic will basically just etch it vertically. So this is basically undesired factor of this wet etching. Dry etching is basically is a plasma based. So it can be of course selective, and because this is bombarding, so it will be anisotropic. It will etch vertically, not the laterally like wet etching. So um, reactive ion etching, these chemicals are basically like chlorofluorocarbons. They flow into this chamber, and this is basically some potential is applied here, RF power supply. So this is basically anode, and this is cathode, a negative terminal, positive terminal, and its surface area is less. So what will happen? Plasma sheath will form here. So plasma is conducting, but inside this sheath is not, it is basically kind of, it's hindering the movement of carriers, right? Movement of electrons and ions. So in case of plasma, electron and ions are the carriers. So of course, electron have a smaller mass, So they will accelerate it to higher energies, and they will again, bombard on the surface and create the ions and radicals, right? So these ions and radicals will be inside the plasma. So of course they will hit the surface also, but this they will hit the gas particles also. And these gas particles will basically, or gas molecules, atoms, they will form ions, right? So there are two types of species that are formed: a positive ions, right, which they accelerate because they are positive ions, they will hit the surface, and another is reactive radicals, right? So these are molecular fragment, and these radicals are basically, they are similar to the chemical etching, so they are usually isotropic, and these bombardment ions is basically is anisotropic etching. So basically you can control these two, and you can have the combination of anisotropy and the selectivity. So this is reactive ion etching, and we already discussed the wet etching and the dry etching. So the last topic for this one is the for fabrication is metallization. So how the metallization is done? If you see here, this is your wafer, right? Then in this case also you use plasma only. So in plasma you have the sputtering gas, usually the inert gases, argon, they are ionized by the plasma, and they will hit the surface, right? So this surface can be, any metal, aluminum, copper, right? And once this argon ions, they hit the surface, these metals are knocked out, and then when these metals are knocked out, they will deposit on the wafer, right? But when these metal atoms are knocked out, they will move, right? They will randomly move. So what is done basically, a low pressure is maintained, so that their mean free path is longer compared to the gap between the wafer and the source, right? So that they basically deposit on the wafer hold. And for example, gold is used for gallium arsenide, and aluminum is used for silicon. But recently what is done basically, the copper is also, sorry, this is this copper is basically used for silicon, but the copper has tendency to diffuse in silicon. So what is done, it is not directly deposited on silicon. The silicon layer is deposited with a titanium layer, then on top copper is electroplated. So this is another process basically. So if you see this picture here, this ions are hitting the target. Target is made up of metal, and this is knocking out these metals, right? And these metals are getting deposited on the wafer. So this is also used for interconnect metallization, right? And another thing is that once you have these interconnects ready, let's say you have this whole wafer is again, made the device, made the interconnect, right? Then on top, silicon nitride layer is deposited, right? And in case of gallium arsenide also, some kind of cap layer is deposited, because see, at high temperature this arsenic has a tendency to go out, right? So that will of course create the defects, right? So some kind of cap layer is deposited on the final product, so everything is covered and safe. Okay, with that we have basically reviewed the fabrication process. So we have discussed the metallization, the thermal diffusion or thermal oxidation, ion implantation, then rapid thermal processing, and the photolithography. So this is a brief review. So I will close here. Okay, let me stop recording.